Hello everybody. I will start a series of videos talking about the Newtonian gravitational force. And in these videos, we will discuss how to use the gravitational force to solve some exercises and problems, and what are the skills needed to do so. Throughout the videos, we will talk about things like gravity force. We will talk about the gravitational field strength. We'll talk about the potential field and the potential energy. Now, to remind you, the Newtonian gravitational law is valid for point masses. That's for small size masses. Now, what does it mean, small size? You can think of it in practical term as when the sizes of these masses is so small compared to the distance between the two masses, then we can use the form that's written by Newton, saying that the force of gravity is equal to some constant called the gravitational universal constant, proportional to the multiplication of the two masses, mass 1 times mass 2 in a question, and inversely proportional to the distance squared. Now that's the magnitude of the gravitational force. So the first comment you should note that this expression originally is valid for point masses. That's for small size masses. Second thing, there are really two forces in the question: action and reaction forces. So mass number 1 in this picture is attracting mass number 2 by a force, let's call it F2, while mass number 2 is attracting mass number 1 by a force we call F1. Now the magnitude of the two forces are equal, but the directions are opposite. And of course, the force of gravity is always attractive according to Newton's gravitational law. In this video, we'll try to set up notation to be used later in other videos. So let's imagine we have two masses somewhere in space, and let's start with a simple case where mass number 1 is located at the origin, while mass number 2 is somewhere in space. Now, the vector that's connecting mass number 1 to mass number 2, or from the origin to mass number 2, that's the famous position vector that we call r vector. Now, let's think of mass number 2 to be the one that we are interested in, and we want to study its motion. Now, let's think about what is the force on mass number 2. Now, according to the gravitational law, the force acting on mass number 2 is, let's think about first magnitude, is equal to the constant g times mass number 1 multiplied by mass number 2 divided by the length of the position vector square. Now, to include direction, we will add minus sign, so there's a negative sign, times r unit vector. Now, r unit vector is a vector which has the same direction as the position vector. However, it has a magnitude of 1. Now, this expression gives the magnitude and direction of the gravitational force acting on mass number 2. And it's clearly that the force acting on mass number 2 should go opposite to the position vector, so it goes to the direction of mass number 1. Now, to remind you, r unit vector, or in general any unit vector, is defined to be the vector in the case of r unit vector is equal to r vector, the position vector, divided by its magnitude. Now, this will give us a unit vector, which is clearly has a magnitude of 1. R vector has a magnitude of r, and denominator is r, so the magnitude of r unit vector is 1. Now, r unit vector has the same direction as r vector, and another thing to note that the unit vector r is dimensionless because r vector has the units of length and the denominator also has units of length. So in general, all unit vectors are dimensionless. Now we can define also what's called the gravitational field strength, G vector. And by that we mean, you think of mass number 1 as a source that's creating the gravitational field everywhere in space. Now, the gravitational field produced by mass number 1 is minus the universal constant times mass number 1 divided by r square, r unit vector. Now, this is similar to the electric field produced by a charge. Now, if we substitute r unit vector by the upper definition, it's r vector divided by r magnitude, so we can rewrite the field strength G in this form. The force will simply be mass number 2 times the field strength G, which is equal to the same old expression, but we wrote it slightly different using r vector, and there is in the denominator an additional r magnitude. So we got r cubed in the denominator of this expression. The gravitational potential energy between the two masses of the system is defined to be minus g mass 1 mass 2 divided by r, the distance between the two masses. Now note that the gravitational potential energy is negative, and the minus sign, this comes from the definition of the potential energy and from taking the reference point to be at infinite distance. So this means as r goes to infinity, so the two masses are far away from each other, the potential energy approaches 0. Now when the two masses are closer, the potential energy becomes more negative. And that's because the force of gravity is an attractive force that's pushing the masses closer together and thus reducing their potential energy while increasing their kinetic energy. Another quantity we define is called the gravitational potential, V of R. Now, V of R also resembles the electric potential in electricity and is defined to be minus G mass number 1 over R. So again, we think of mass number 1 as a source that is creating this gravitational potential. Now, the force is related to the potential energy by this famous relation. The force is equal to minus the gradient operator acting on the potential. Now, let me just say one thing, make one comment. I mean, the level of these videos should be suitable to university students in physics, in mathematics, and in engineering. For other students, they are, of course, welcome to watch the videos. And if you have any difficulty in the mathematics, please consult other easier videos on the subject. Now let's move mass number 1 from the origin to somewhere else in space. So now let's put mass number 1, mass number 2 in space. And now let's rewrite things using the new locations. How do we write the force in this case? Now, because mass number 1 and mass number 2 are shown here, so we can define the position vectors for these masses. So mass number 1 has a position vector called R1, while mass number 2 has a position vector called R2. Now, what we are interested in is the red vector. The red vector is the vector that connects mass 1 to mass 2. Now, how can you write this vector using R1 and R2? That would be easy exercise. Try just to trace these vectors. So R1 is moving like this. The red vector is moving from mass 1 to mass 2. And R2 is moving from the origin to mass number 2. So it's clearly that vector R1 plus the red vector should equal vector R2. Now by moving R1 to the other side, so the red vector is nothing but vector R2 minus vector R1. Now, with this, we can write the force acting on mass number 2. It's minus g mass 1 times mass 2 divided by the distance between the two masses. That's the red vector. So it's the length of the red vector cubed times the red vector. Now for the potential energy, again, it's written as a minus g mass 1 mass 2 divided by the distance. That's the length of the red vector. Now, how can you find the length of the red vector? The length of the red vector is easily found by using this technique. A vector, if you want to find the magnitude of any vector, you just dot product this vector with itself. This will create the vector square magnitude, and then you take the square root. So to find the magnitude of any vector, we will use this relation. Now we take r1 minus r2 minus r1 vector dot itself. Now distribute the vectors with the dot product, then you will get r2 vector dot r2 vector, and this will give us the magnitude of r2 square. Negative or minus r1 dot minus r1 will give us r1 square, and then we will get the mixing terms, two terms from the mixing, so we will get minus 2 magnitude of r1 magnitude of r2 times cosine the angle between the two vectors. Now by looking at the shape again, the angle between the two vectors I call theta. So this is the magnitude of the red vector. So in this case, the potential energy could be written as minus these constants divided by the square root of this expression. So we almost finished this video, but before we leave, I want to talk about two problems or concerns. Concern number one is that the gravitational law that we wrote originally is valid for small masses, for point masses, for small size masses. So now the question is, if we have big size masses, and that's an important question because, for example, if you think about Earth and attracting other objects, now you may say Earth is a huge object. So what form should I use for the gravitational force and potential energy? So this will be our first concern, and we'll try to answer this question in the next few videos. But the answer in general is the form will be dependent on the shape of the mass, the big mass, and the density distribution of the mass inside this shape. Of course, a similar concern also arises in electricity, in electrostatics, for the electric field and the electric potential energy. Concern number two is, now if you think about this problem, we have two masses. Now, the two masses, they are attracting each other. So mass number one will accelerate, mass two will also accelerate. Both masses will move and will trace orbits or paths. So that's called a two-body problem. How would you study a two-body problem? Now, in one of the next videos, I will explain how to reduce a two-body problem in gravity to a simple one-body problem to make things easier to handle. Thank you for watching, and see you in the next video on the same topic of Newtonian gravitational force.